There are two acid derivatives that contain nitrogen that can also be reduced. We have the amide functional group and we have the nitrile. So if we add a hydride as a reactant for both of those, we can do the same exact thing. And what happens in both of these cases is exactly what you'd expect. You're coming in with the hydride and adding to the partial positive carbon. So in the nitrile we have a partial positive carbon just like we do in the carbonyl, and we're kicking up the electrons onto the more electronegative atom there. So if we wanted to do a reduction of both of these groups, functional groups that have a bond to a nitrogen on it, what we will see in the end is that we are reducing them not to an alcohol as in the previous example, but to an amine. So the carbon-nitrogen bond is stronger than the carbon-oxygen bond, and that is the bond that remains. And so in this case, we are not keeping the carbonyl. We are actually reducing in the first step to a CN double bond, and under basic conditions then this will not be protonated and there'll be a negative charge on there. And so it looks like an imine, except with a negative charge on there. So after this adds, we'll have to have some sort of a rearrangement where we're going to deprotonate here and end up forming a CN double bond. Note that this CN double bond is the same oxidation state as the aldehyde in the previous example. But again, because carbon-nitrogen bonds are stronger, we end up with a nitrogen remaining and the oxygen being removed. So actually in both cases, if we wanted to stop at this state and not go all the way on to the amine, we could add what we added to the ester above, and that is diisobutyl aluminum hydride. So in both of these cases, if you wanted to stop at this state, you'd add diisobutyl aluminum hydride. And the reason you would want to stop at that state is that now you could add water in the presence of acid, H3O, and that would then convert this carbon-nitrogen double bond into a carbon-oxygen double bond. So you're adding an excess of water, and that converts it into the stable neutral aldehyde molecule. So under the original conditions with the diisobutyl aluminum hydride, we go to the intermediate, and then when we add water, the oxygen source, then we end up converting it to the aldehyde. So this is a good way to convert both of these groups to an aldehyde. So either one of these, if you added in step 1 diisobutyl aluminum hydride and in step 2 H3O, you would convert them to an aldehyde. If you wanted to go all the way to the amine, then you would use a stronger hydride reducing agent, and we would actually use the same one that we used in the examples above, lithium aluminum hydride. And so either one of these, the amide or the nitrile, can be converted all the way to the amine by adding lithium aluminum hydride followed by H3O. Also, this particular reaction will go with a slightly weaker reducing agent, sodium borohydride. So you can use lithium aluminum hydride for this or sodium borohydride for this. So if you wanted to make an aldehyde as a final product, you could convert either of these functional groups into that. If you wanted to make an amine as a final product, then either of these functional groups can be converted into the amine as well.